Good morning and good afternoon, ladies and gentlemen. It's indeed a many unique opportunity for me to introduce Dr. Heinrich Fragner. And this is the TSU Mini-CubeSat webinar number 9. And we are really lucky to have Dr. Fragner with us to talk about PRETTY. PRETTY is definitely the CubeSat mission for GNSS reflectometry and interferometry. And as you know, Hans, and we Taiwan also have a similar mission. So a lot of scholars and students, they are also in line and they looking for what you have done, and hopefully that we can look for more dialogue and discussion and even future cooperation. And Dr. Heinrich Fragner is now with Rock Space GmbH, and it's a company that dedicated to a lot of space instrument and technology. And Heinz, if you are ready, and I will, the floor is yours. Okay.
So thank you very much for giving me the opportunity to present our PRETTY project and passive reflectometry project. And thank you for the introduction, and good afternoon to Taiwan. So here in Europe, it's still in the morning. And right at the beginning of my speech, I would like to introduce, I hope you can all see the screen and technical stuff is working. But
yes, it's fine.
Yes,
good.
Okay,
it's very good.
Yeah. So you are well aware about passive reflectometry, and there are already a lot of missions ongoing and planned, and also experimental flights and airborne models. And the peculiarity of the PRETTY mission is the interferometric method. So the interferometric method is different a little bit to what you normally know about the passive reflectometry, where you generate a local code replica inside the receiving spacecraft. And with the interferometric method, you will not do such a local code replica, but you receive the signal transmitted and the signal reflected on the Earth's surface at the same time, and do a correlation of these two signals. So this is a little bit different to what you normally do with local code replica. RUAG Space is a supplier for payloads and since almost 20 years in the European space market. And for this particular project, we have set up a consortium consisting of university and research institutes located here in Austria. So you can see on the right side of this first slide, we work together with Technical University Graz, which is located in the south of Austria. And they have already launched 2 micro or nano satellites. So maybe you know about the BRIGHT mission, which is a star observing mission, and OPSAT, which is an ESA mission with a signal processing and SDR processor on board. Cyberstorff Laboratories is known for their capabilities in the area of radiation monitoring and dosimetry. And they provide to the PRETTY satellite a secondary payload, which is a radiation monitor detecting heavy ions and also total dose measurements. So PRETTY will have 2 payloads on board. Within this talk, I focus only on the passive reflectometry. This study is financed by the European Space Agency. So also all the requirements and quality expectations on the missions are based on the set requirements provided by ESA. In addition, we have the access to scientists in ESA, because in particular Manuel Martinera has basically invented the principle of the interferometric method and also patented several years ago. And so we have, he's working at ESA, and we are in close contact with planning and setting up the mission. So now I would like to speak about what are basically the advantages of the interferometric approach. So the idea to make local code replica is in some way much more convenient, because this is very similar to typical GNSS receivers. So you can even operate normal GNSS receivers in order to get passive reflectometry working. But there are advantages why we should, or why it is interesting to perform this interferometric method. I'm sorry about this laser pointer. I do not move it. I don't know why it moves, but okay, just ignore it. Yeah, seems to be some weird moving around of this laser pointer. Okay, so the point is that this interferometric approach works not only with GPS signals, but also with other signals of opportunity. And we do not know or have to know this modulation. So this means any signal which is provided by a spacecraft, this can be a telecommunication satellite, it can be geostationary, or medium Earth observation orbit. Any signal, any satellite that transmits signals can be used, because we detect both the direct and the reflected signal and do the correlation there. So this is in particular interesting because with that knowing, we can also switch to different frequency bands. When we exploit navigation satellites only, we are limited to the traditional navigation bands, so L1, L2, E5. But for navigation signals, there is a broad range of frequency bands which are in use today. And in addition, these signals also have a higher transmit power. So one of the problems you are probably well aware is that navigation satellites transmit their signals with a very low power. And therefore you need a relatively long integration time, coherent integration time, in order to raise the reflected signal above the noise floor and to extract the according signal from this reflected transmission. So these are two very strong advantages. Because also with the different frequency bands, you can do different observations. So for example, the entry depth in eyes is a different one depending on the frequency. The response to moisture is a different one depending on the frequency band. So there are a lot of observations which can be improved or seen within different frequency bands. Then what we also do in PRETTY is that we focus on grazing angles. This means that that we look right to the horizon of the Earth. I will show this a little bit later. And there is the space vehicles that rise above the horizon first will not have a reflection, and then so it's basically at the beginning it's more a radio occultation, and then it turns to become a reflection of above a certain threshold. So maybe you are aware that Ruhrg also has built one of the most, I think it's even the first radio occultation instrument which is in operation since many years. So the GRASS instrument on Matlab satellite. And this is focusing on radio occultation. So for us, the reflection, so passive reflection, is basically the natural proceeding from radio occultation to reflection. Another advantage of the interferometric approach is that both signals, so the signals which is received directly from the transmitter and the signal which is received via the reflection on Earth by the transmitter, traverse through the atmosphere in different heights. So this means you can differentiate the traversation of the signal between two different atmosphere heights or altitudes. Yeah, so this is another advantage. Maybe it becomes a little bit more clear in the next slide when I can show this on the images. And PRETTY will be actually the first satellite in orbit that implements this interferometric approach. So we are really eager in seeing how to evaluate this data and how to extract all this information and in this new way, and what additional information we can see from there. Okay. So what are the objectives of the PRETTY mission? Again, the laser pointer, I really don't know what it's doing here. Please ignore it. So the PRETTY mission aims at grazing angles, as said before. So we do not look directly nadir for reflections, but look very close to the horizon. So we limit ourselves to the elevation angles of less than 15 degrees. Our observation band is the L5 band. So we originally intended to use the L1 band, but we in contact with ESA, with Manuel Martinera, we now decided to switch to the L5 band because due to the longer wavelengths, we see that there is a clear advantage as the coherent integration time can be kept longer. So we expect a higher signal-to-noise ratio due to longer integrations when we use the L5 band compared to the L1 band. So generally, the signal-to-noise ratio of the interferometric method will be worse than with the clean replica code, of course, because not only the signal which is reflected is disturbed by noise, but also the direct measurement signal is disturbed by noise. So this is one clear disadvantage of the interferometric method, in particular when you are using signals with a very low SNR or very low power level at the transmitter already. The primary objective of the PRETTY mission is altimetry. So our signal processing core is capable of providing all scatterometry information. So we automatically calculate DDMs on board and download them. So in order to minimize the data volume needed on the downlink. But the primary objective of, as said, is altimetry measurement. So I will today not present any scatterometry evaluation of data, as this is not in scope of the PRETTY mission. But as said, we will provide the information, and I'm looking forward where the scientists will capture this data using and deducing some information from based on this, thinking that there is interest in the L5 data and in the fact that it's interferometric data, which can provide new insight. Okay, so on this image you see a little bit in a schematic how the setup is. So okay, it's funny, I have on every slide I have this red spot. Please ignore the red spot. I hope you can see also the mouse pointer.
No problem. Yeah.
You have here our PRETTY receiver and here the transmitter from the GNSS space vehicle, and you have a gain antenna which is looking to the horizon, and therefore it covers both the direct and the reflected signal. And here you can see that both beams traverse through the atmosphere, or at low angles at least they will traverse through the atmosphere. So we have an influence of the atmosphere on the signal, which is directly and reflected. And therefore, if you differentiate both signals to each other, you can deduce information rather on the two different atmosphere layers than on the, if you have only the single pass through the atmosphere and compare it to an undisturbed signal. So this means in PRETTY we have also the possibility to do local code replica, and we will be very interested in what is the difference between the correlation peak in the local code replica and in the reflected signal. So this comparison will help us to understand the influences between the fact that the signals traverse between along the atmosphere through two different layers. On the right picture, you see a little bit improvement of the antenna, because what we actually have, I have done some slides later on, the antenna is a patch antenna, and we have therefore the capability to implement some kind of beam steering. This means the same antenna has two gains. One gain is optimized for receiving the reflected signal, and the other antenna beam is optimized for receiving the direct signal. So the right one is actually what will be implemented, and the left one is the original plan. So this was an evolution within the last few months, where we have decided to implement this electronic beam steering with the same antenna. Yeah, on this slide, waiting for the annoying red spot. Okay, maybe we have luck this time. No, here it is. This time we have the block diagram of the passive reflectometer. So it's very straightforward. From top left, you have the antenna entry, which is the antenna is almost pointing towards horizon. Then we have a standard RF front end, I would say, with a low noise amplifier, according filtering and analog to digital conversion. Of course, the front end has to be designed in order to keep the lowest possible or get the lowest possible noise figure, because any noise we add here in the front end, of course, degrades the final SNR, and SNR will be a key issue. So to optimize the SNR at the detection circuitry. Then, as said on the this signal is then split, and one part of the signal is directly fed to a correlator, which is 200 taps long. It works in the time domain, and the second pass of the signal coming from the front end is put into a time delay, meaning this time delay will compensate for the different runtime length of the reflected signal. So the reflected signal has obviously several kilometers longer runtime, and therefore this time has to be compensated and before it is sent to the correlator. And inside the correlator, then the adjusted signals will be correlated, and you get the pure signal form of the correct correlation peak. As already said, we have also a local code replica implemented for on-ground testing purposes, basically. But of course, we can also use that during our observations in space. So we can select whether the antenna signal is fed into the correlator for the interferometric method, or if the local code replica is fed into the correlator to implement the standard reflectometry approach. After the correlator, we have an integrator. This means we can configure this integrator to specific times, how long coherent integration will be done and how long incoherent integration will be done. So this can be set from ground, and after this the telemetry, the results are dumped via telemetry to ground. So this is the coarse block diagram, and a bit more detailed diagram we can see on this slide. This is the block diagram of the processing core, which is designed to have two antenna inputs. So originally the design of the processing core is not limited to the grazing mode, so meaning just low elevation angles, but you can use it also with an up-looking and the down-looking antenna as well. And of course, we need the second input also for the local code replica input. So the first stage is that each path is used for a final downmix. So the architecture foresees an intermediate frequency on the front end, and the last or the final downmix is done in the digital domain. And after this, there is a bandwidth selection, which depends basically on the GPS or Galileo or whatever band to be used. So the L1 band is a very narrow band. The L5 band will be much wider. So there is a configurable FIR filter in order to select the optimum bandwidth. Then we have a power measurement system which adapts actually to the noise level, to the background noise level. As you know, the GNSS signals are below the general noise level, and the gain of the will be digital controlled by this power measurement system. Then here we have the adjustable delay in one path of the antenna, and afterwards the both paths are combined within the correlator. The next block is available inside the processing core not only one time, but it's implemented 5 times. So this means in parallel there are the processing is done for 5 different Doppler bins. So this means to generate these delayed Doppler maps, we do not need only the 200 taps of the correlator, the length, but also to have a different Doppler running then the final integration, and that is done in this dotted square. So this is implemented 5 times in the correlator ASIC. At the end, you have then the result buffer where all data is stored and then dumped to the telemetry. On this slide, you can see some observation statistics. For us, it's important to know how many observations we will have and how long these observations will take. So for us, the most interesting observations are which have a long track above or a long ground track. So we aim for long observation periods where we can, this allows the most interesting insight in the altimetry over oceans, open oceans, which is the main interest of our scientific partners. And for this purpose, you see, depending on the flight direction, so 0 degree is in flight direction versus plus and minus 180 is anti-flight direction. You see that the least observations we can see perpendicular to the flight direction. But on the other hand, when we look at the duration of the observations, we see that the longest durations of observation we see also perpendicular to flight direction. So in order to cope with the requirement to observe as long as possible tracks, we will do our main observation in perpendicular to flight direction, and we aim to observe not only GPS but or observe mainly Galileo E5 observations and the L5 observations. So in order to get as many as possible observations. So because the statistic is a little bit poor anyway, but by using or exploiting 2 constellations in orbit, we can increase that. So here is a slide that shows our considerations with respect or argumentation why we change from L1 to L5. As said, the L1 band, we can build a little bit higher gain antenna on the small footprint of a CubeSat satellite than on the L5 antenna, because the gain is depending on the distance of the arrays and also on the wavelengths of the signal. So L5 has a longer wavelength, therefore the gain which we can achieve with a 30 centimeter satellite is even lower than for L1. In addition, L5 has a little bit less of transmit power than the L1, so these are basically 2 disadvantages to the L5. But as said, the advantage of L5 is that we can have longer integration times. And this diagram on the right side shows the expected SNR gain by increasing the coherent observation times. this is not only a theoretical model, but these figures have been evaluated by Manuel Martinera together with already available in-orbit flight data. So we are quite confident that this plot will hold true and that we can really increase coherent integration time from 20 milliseconds, which was originally planned in the L1 band, to up to 50 or even 100 milliseconds, and therefore improve again the signal-to-noise ratio by 10 to 15 dB. So, as you know, Pretty is not yet in orbit. So for the time being, we have to limit ourselves on observations which we do on ground. Here you have an aerial view of our test setup, where I show you now some images from first results. So on the right-hand side, you can see the Danube River. And on the left-hand side, indicated by a red circle, we have our measurement location. And this measurement location is elevated roughly 120 meters above the level from the Danube River. So it is actually not a perfect setup because the distance is quite close to the Danube River, but it was yeah, the first choice, and we were actually also a bit limited by traveling during the COVID period. So this was a very close location, which was affordable at this time. The important thing why for the interferometric method, it is in particular not so easy if you're very close to the reflection. I show you on this slide. So basically, this is an autocorrelation. So what you can see here is due to the fact that you feed both signals, so direct and reflected signals, via the same antenna path, you have not only a correlation peak at the point where you have the reflection and the direct signal, but also you have an autocorrelation of the direct signal. This means, or an autocorrelation of all signals which you basically receive via the antenna. So, and this is exactly the autocorrelation you can see here. So this means when you switch on your reception antenna and correlate this signal with itself, you will get, of course, a peak indicating the autocorrelation of the signal inside the bandwidth of your antenna. This is not. This is even true if there is no signal at all, but only the noise. So you will always get a peak. If it is a pure white, pure noise, then you get a peak which is dependent in its width on the bandwidth of your RF front end. But in this case, you also get a peak which is the shape of all GPS, GLONASS, Baidu signals which are available. They all mix together and have a certain shape in the autocorrelation figure. And this is basically what you observe in a measurement when you just do this autocorrelation. So here is a little bit more details on this. So the left plot indicates an Matlab or numerical simulation, what is expected when you do an autocorrelation in this, at the time it was the L1 band, in this L1 band. And on the right-hand side, it is compared with the output from our processing core, and we consider it is quite a good matching of these two figures. There are some deviations, in particular very close to the zero time. We have some residuals which are probably from or which can be explained by the thermal noise. So, and the point why I have to show this is, of course, that if the peak of the reflected signal is now close to the autocorrelation peak, then it will be very difficult to distinguish between the reflection peak and the autocorrelation peak, because the autocorrelation peak is actually much larger in amplitude than the reflection peak. So we have a loss of some 15 or 20 dB due to the reflection. And so the peak of the reflection will vanish in the autocorrelation peak if the separation between the direct and reflected signal, or the distance difference between the direct and reflected signal are too little. And this is exactly what we have observed also in this location. So here on this picture you can see the reception of the signal via the open loop, via the local code replica approach. So we can prove with that the front end works well, and the curves we receive are exactly as we expect. What you can see here is a variation or a drift along time in the correlation peak. So you see on the horizontal axis there is the time of measurement. So starting at it runs about 2 minutes, and during these 2 minutes you plot these correlation tabs from the correlator, and you see that it is not stable over time at a certain point, but it's varying, and this variation is caused by the drift of the oscillator. So we have used for this experiment a very low cost oscillator, which has according drifts. This is relevant for the local code replica approach, but for the interferometric approach, it is in the first range not so important, because the direct and the reflected signal are in the same way affected by the oscillator error, so it compensates. But that's just in the first order of approach that it is compensating. So of course, for the flight units, we will have a much better oscillator. But as said, for the interferometric method, it is not such a big deal, the oscillator, than for the local code replica approach. So, and here is a short summary of the findings during this local code replica. So I already explained briefly the variation in the clock drift caused this. The variation in the clock caused this drift, and the pictures you saw are in an open loop tracking, so there is no feedback loop implement, so that this drift would be compensated by a feedback loop. So and now I come to the last image from this measurement campaign, which was actually the first, let's say, interferometric detected correlation peak. So we were quite happy after having this the first time. So although it looks a bit unspectacular, but as we had the most joy with this image, I wanted to show you that. So what you can see actually is here on again, as you see now, a stable over time, a stable correlation peak. So we have again a measurement time of 2 minutes, and all DDMs or all correlations observed during this time are stable at 200-meter delay. And what you can see is that the lower boundary of this correlation curves is quite stable, so there is no oscillation. But on the top line, you see some kind of oscillation. So that means that for some seconds, the red line goes further to further delays, and then for 10 seconds it goes to lower delays. So I don't know whether you can see my mouse pointer, but these these peaks here on the top, these are what I'm referring to. And the explanation for these peaks is that the Doppler on the direct and the reflected signal are slightly different. So this means if you do these geometric considerations on the reflection, on the transmitter side, the reflection and the reception, you have a slightly different Doppler on these two pathways. So this is expected, and if you compensate now for just for the common Doppler, then you will observe such an interference in the phase between the direct and the reflected signal. So the reflection will, for one time, lower the amplitude of the direct signal, and at another time it will increase the amplitude of the reflected of the direct signal. So basically, this is totally what is expected, and is a clear indication that you have a multipath reception of these signals here. So then, of course, we had to do some mathematics and on this data which we have observed in order to prove that. And as said, please be aware that this that you see it only as a variation in the width of the received amplitude is a matter of the fact that the setup is so close, so that we have just I think 150 or 200 meters in difference between the direct and reflected signal. And when we do the same experiment, let's say from an aeroplane or from a satellite, the delay will be much more, so it will be in the range of kilometers. And then there is no overlap between the autocorrelation and the cross correlation between the received and the between the direct and the reflected signal. So that's a consequence of the chosen setup. And as soon as we do our next experiments based on an aeroplane, we expect that these two correlation, or the cross correlation and the autocorrelation peak, are well separated, and we can observe only the cross correlation peak isolated and deduce the information from that. So as said, there is a little bit of mathematics has been done, showing on the bottom line all correlation results, and they are then mixed with the expected Doppler frequency. So we can see here the secondary peak at some occasions to come up. So we have the main peak here at shortly before 200 meters, and the secondary peak here around 300 meters. And as said, so the the close distance of only 100 meters between these two peaks does not allow for a more better separation. But looking at this evaluation in Matlab gives a good impression on how it will look when we enter the aeroplane. Okay, so then some further details on the technical work. This is basically the new antenna design. So as I said, it's a patch antenna. It's a very flat design, and the size is approximately 8 centimeters by 8 centimeters. And therefore, we cannot accommodate more than a 2x1 array. So if we had a larger satellite, we could separate the arrays further and obtain much higher gains, what would be quite beneficial in order to increase the signal-to-noise ratio. But due to the fact that we are here on a 3U CubeSat, that's the best we can do. We have designed, or Technical University actually has designed this antenna with an estimated gain of 8 to 9 dB, which is in the meantime already proven in the measurement, anechoic measurement chamber, so that the design went well. And yeah, we had to adopt some details in the front end, but basically this is just optimizing the matching for the L5. Otherwise, it will just be reprogrammed. This is a complete overview of the pretty spacecraft. The spacecraft as such is inherited from a mission called OPSAT. As said, Technical University Graz is operating since December 2020, this OPSAT mission. Or let's say ESA operates this mission, so this is also an ESA mission, and TU Graz has provided the satellite, and several components which are already used on the OPSAT mission will be reused in the PRETTY mission. So we have a primary radio in the VHF range on the top. Then we have the instruments, or the onboard computer and navigation computer for AOCS. We have the battery pack. We have the power supplies. We have what you cannot see on this display, but on the slide, I think for the announcement, it is a 2-wing folded solar array arrangement. So that there is some power consumed by these signal processing boards, which are called SEP. So we have a code redundancy with 2 system-on-chip FPGAs hosting an ARM processor, which are a little bit power hungry. So we need a larger solar area. Then we have a commercial off-the-shelf GPS receiver in order to get all the almanac and ephemerid data to select the observation points and calculate the best possible tracks in space. So this is nothing which needs an interaction from ground to guide the satellite, but it is normally autonomously chosen inside the satellite. And then we have the reaction wheels. Then we have a secondary radio, which is the S-band radio, which works only in one direction so the S-band patch antenna is in the -z direction and is not suitable for establishing the first contact, but is very well suitable, of course, to implement some higher data rate on the space-to-ground interface. And then we have the secondary payload, which is the dosimeter, which is inside the Mini-CubeSat, and as said, it hosts a dosimeter with different shielding thicknesses, with different technologies. So there is a GATFET and an FG-DOS dosimeter. Then we have particle detectors. These have been developed or are developed by Cyberstorff, which have a close cooperation also with CERN, where they get inputs for the design of this dosimeter, in particular of the particle detector. So this is a block diagram of the satellite. It is makes heavy use of third-party products, so we do not intend to invent or design parts in the spacecraft that are available on the market. So the cost pressure for designing it our own would be too high, and we rely on available products and that are already space proven. So we really focus on the payloads in this mission. You have, as said here, also the UHF antenna connected via third-party communication interface to the onboard computer. Then you have a bus system inside the complete satellite or spacecraft, which is based on CAN CSP protocol, and you have as a secondary interface also an SPI interface connected to most components. But as I said, that's a backup system, or considered as a backup system. Then you can see here the patch antenna is connected. It's the patch antenna on the -z interface is connected to the S-band transceiver and also connected to the nanomines, which are the onboard computer. The power modules, so EPS motherboard connected with solar panels and batteries. And then you have the payload section, where you have the dosimeter payload, which is connected to the same processing FPGA. So this, as said, is a system on chip module with an ARM processor and running an operating system. And this will collect also the data from the dosimeter payload and then provide this data via the CAN bus to the onboard computer for downlink. The processing core is a separate PCB from the reflectometer front end. So the reflectometer front end is, as said, a part which is used normally in telecom area and which has a wide variety of configurability. So we can basically the front end adapt to different frequencies and different bandwidth. And we have now selected the L5 antenna and bandwidth. So the antenna is indicated here. It is connected to the front end. Here it is digitized, and the data is passed to the SEP, so the system on chip processing core hosting the correlator. Here on this last slide, you can see the geometric setup. So the reflection was observed here on Leopoldsberg, roughly 250 meters elevated from the Danube River, and the reflections coming from the Danube River itself. Thank you for your attention.
Okay, thank you very much for the wonderful presentation, and we enjoyed very much. Just one question for myself: when do you expect to launch this pretty CubeSat?
Yeah, so we are currently in the negotiations for the launch, and we expect it to be launched in Q3 next year.
Okay, good. And good luck then. Okay, so now we open the floor for questions. I wonder any question, please speak. Please go ahead. This is indeed a many unique opportunity to have the first-hand information about this many important mission using interferometry technology to process GNSS signal. Okay, please. Hello, Suzy, please.
Yes, can you hear me?
Yes.
Yeah. First, thank you very much for your great presentation, and it's very exciting to see this new satellite mission. So my question is, so should I expect that we now will have continuous RO and R observations from this satellite, and so in terms of the data distribution or the frequency of the data, can you briefly describe that? Yeah. What the data type?
Yeah. So this is not a commercial mission. This is clearly declared as a tech demonstrator mission. So the purpose is to show the effectiveness of the grazing altimetry using the interferometric method. So there are some, let's say, new aspects in this respect, and which is not covered by other missions, and focuses, as said, on the altimetry. But we do not intend to commercialize or these observations. They can be can be made available, whoever is interested in them. But also the number of observations is limited due to the architecture of the spacecraft. So we have power constraints, so we will not have, let's say, a reduced observation times compared to the observation possibilities. So in order to make really a full-scale mission where you, with the goal to gather as much data and to commercialize this, you would have to go for a larger spacecraft with more processing power and more energy power, or a higher number of spacecrafts, of course, is an alternative.
Okay, are there any other questions? Please raise your hand. Hans, you mentioned about the beam steering. Can you elaborate it a little?
The beam original concept was, as said, without beam steering, and to do the beam steering actually by movement of the spacecraft itself. So leaving it to point to the horizon. And for this purpose, we have now changed this. So there is a 2-patch array of L5 antenna, and we have a combined beam steering. So one axis is controlled via the spacecraft movement along the observation track, and the second axis, so the perpendicular axis, is controlled via electronic beam steering. So meaning that in the digital domain, the 2 patches are fed separately into the digital domain of the processing core, and inside the digital processing area, the beam steering is implemented.
would you be able to change the polarization of the antenna by using beam steering?
No. The polarization of the antenna is given by its geometry, and the advantage of the grazing mode observations is that the direct and the reflected signal are mainly in the RHCP area. So this means the steeper your reflection angle is, the more you shift the reflection polarization from RHCP to LHCP. So for nadir pointing, you have LHCP, while for grazing measurements, you have RHCP.
Yes, okay. So are there any other questions about this presentation? Okay, yes, Professor Yang again. Yes.
Yeah, sorry for another maybe also a little bit simple question. So so in terms of the so compared to the current reflectometry, the technique, so for this new technique, should we expect, for example, the delayed or Doppler shift, the resolution will be different?
Yeah, you need to consider that the shift between the direct and the reflected signal. Maybe you can mute because there's a strong echo. Thank you. So you have to expect that the Doppler of the direct and the delayed signal are different. But what we do, of course, is to calculate for both signal paths the Doppler and compensate it accordingly inside the processing core.
Thank you.
Okay, any other question on this? If no, then I would like to take this opportunity to thank Dr. Fragner again for a wonderful presentation. And we look forward to, see each other originally, but unfortunately due to the COVID. But in any case, we will keep in contact and hopefully we can share more information about our CubeSat as well as Triton project, which is a GNSS mission. And we would love to learn any new development from the PRETI. And good luck to the PRETI mission. Okay, and with that, okay.
Thank you very much for your wishes. And I also wish you a good development of your goals and your mission. And I would be really enjoy if this small presentation would be some kind of starting point, hearing from you and maybe seeing you in one of the conferences or reading from you. So I'm really looking forward that we have a positive relationship and a good exchange also in the future.
Okay, thank you. Thanks in here. Okay, and with that, I thank you all the audience for your attending this webinar, and I thank you and goodbye now. Okay, thank you.
Okay. Thank you.
Okay.
Bye.
Thank you very much. Bye.